I guess I can start. So let us very quickly review the hypothesizing, because that will be, we are done with this topic today. So just maybe it's good to use the whiteboard to describe what we've done. So what we have done is, in this topic, is the idea of hypothesis testing, right? Is we make some hypothesis on the population, right? So there's some observation here, right? And someone claim what should be the mu and sigma square, which we will cover today, about sigma square. So you want to test a claim on this thing, and what you're going to do is basically take some sample there, right? And you have some sample, right? And based on the sample, you have measurement of x bar, your s square, and you would try to see if x bar is too far away from mu, what you propose, or it's too far away, you reject, right? That is what you learn the first half of this topic. And second half of the topic is introduction of another population, right? Population. And for the sake of discussion, this already we have population 2, right? And the original population 1, right? And we'll put mu1, right? And this is mu2, sigma 2 square. So the things we care, we cover in the last class is we're trying to see if mu1 is equal to mu2, right? And we are trying to see if the two populations have different mean. And we have studied actually four cases, right? The case 1, right, is the fact that we assume, okay, they're the same, right? And case 2 is that different, okay? And you can see case 2 is a special case, right? Not equal to, include, also equal to as well. And case 3, okay, is not exactly this framework, but actually it's also a special case where each observation is linked, right? So that means that you, instead talking about the same, the null is mu of d is 0, right? And how you define mu of d, how you define d? D is just each observation, di is just x 1i minus x2i, right? So for each observation, right, length, right? Say, suppose this is number 1 and this number 1, right? You care about the difference, right? So that is the d, right? This is called d1, the difference, right? d1 will be x11 minus x21, right? And today is we cover is case 4, right? The case 4 is we talk about proportion, right? Instead of mean, is a special case of binary data, right? Binary data. Okay. We are talking about still pi 1 is equal to pi 2. Okay. And case 4, as you might probably recall, has some flavor of case 1 and case 2, because when you have the mean the same, it does imply the variance the same. So it's somewhat with the case 1. Okay, so that would be something we'll talk about. And the final case today we will also talk about is case 5, right? Which talk about another thing, which is whether sigma 1 square is equal to sigma 2 square. Okay. Here we have an independent population, right? Independent population, right? This is paired population. Okay. And actually only the free is pair, right? Only the free is pair. Okay. All other independent. Okay. Maybe this is better because this is not the feature of this, but except the case 3, everything is independent, right? So that would be, I think, is a better description of what we are doing for the second part. Is that a question? Of course, I'll review the case 1, 2, 3 first before we go. And the question? Go. This is the overview of this topic. So I guess would be fruitful to, since we have it after the weekend, so it's good to quickly spend 5 to 10 minutes to review what we have done. Okay. So here we have 2 samples, and throughout the case, we have to assume the normality assumption holds. So everything is a bell. Okay, so that's the first thing. And here we focus on the case where we don't know the variance. Okay, so that's why we'll be using T.TEST. Okay, we don't know. Okay. And do remind yourself that if, okay, which is where, if we happen to have a good guess of variance, we can use that test. Okay, we can use that test for this one. But in reality, unless you're talking about engineering, right, which you know fairly details, otherwise in business application, usually you would use T, right? But so here, as I said, this is case 1, case 2, case 3, right? And case 4 and case 5. So this is what we are talking. Okay. So let's go to the independent sample, right? Because except the pair sample, this is what we use. Okay. Independent sample, we have 2 populations. They have mean, mu, and sigma 1 square, and this notation, right? I'm going to do the notation, and you have sample mean and variance, okay, and also sample variance, okay. So we assume normality, okay. So this is the difference between 2 means, and this is what we used to know. And this is, we call, what is this slide? It's basically talking about the difference of 2 bell is still a bell. Okay. The idea of this slide, just to remind yourself, I think it's important, is this is red, suppose, right? It means the following, right? If you had some red here and you have some blue, this one, okay, and you pick up a number, you subtract them, what you will get, you get a green, right? It will be this guy. Okay, the sum of the difference will get you the difference of mean, and the variance will be sum of the variance. Okay, so that is something we learned that in our topic 4. So I hope you remember, because why I have this is because although it's 2 samples, right? But the difference of the mean is follow a bell. So we just need to know how we handle bell, right? Although it's 2 samples, right? But when you combine them, it becomes a bell. So we can just use the standard way, just because the difference is a bell, right? So we know how to handle bell in the 1 sample test. So everything you learn from the 1 sample actually will be analog, right? And what we learn here is we don't know, if we know this 2, then we are done, right? Because this is the bell, right? In this bell, then we just say, okay, if the data is either in 2-side test, right? If in the both end, then you reject, right? But the thing is, we don't really know, right? So we have to come up with some estimate of this, okay? And in the case 1, because we assume they're the same, okay? So we can simply estimate the sigma square, okay? And turn out how you estimate this, right? if they're actually the same, there's of course you can use either S1 or S2 would be a good one. Okay? Either these two would be an unbiased estimator. Okay. And you would actually want to pick the most efficient one, right? And turn out to be the most efficient one, turn out to be just the weighted average, right? The weights that used for this will be N1 minus 1, right? The way to use is N2 minus 1. So that's why the weighted average of these two will come up as what we call the pooled sample variance, and that will be our way to do the t-test. Is that clear? Why we end up in this one, right? Because the two samples have the same drawing from the population with the same variance. Okay, so either use S1 square or S2 square would be good, right? But the fact that this is not the best case, so that's why we would be using some kind of combination to handle it the best. Actually, you can see, actually you can prove that it's the most efficient one. But anyway, and that is how you compare performance. That is usually what you do together with this one. Okay, so this is the pool sample, and once you put it into here, right, because they pool the sample, right, and that's become the T. Okay, and just to a reminder that because of you estimate two objects here, so that's why you have to minus 2. Okay? The reason is you have actually estimate two means, so you're minus 2. And today you see when you do ANOVA, you will see you will subtract the number of group from when you look at the T table, F table, or so on. But that is general rule is if you estimate one thing and then you have to subtract 1 from that. Okay, and if you were told what is sigma, then you would have you don't have this problem. But anyway, so I'm not going to go over the example. I think this is good enough. You know how to work on it. Okay, and the second one is simply you don't have the assumption, so that's why you don't have any choice, right? So basically just this use S1, right? And for this you use the unbiased estimator that is supposed to be efficient, right? So there's nothing you can do. The only thing that trouble us, right? There's nothing but just the center case. So only thing that trouble us is this V. What's the degree of freedom? And the formula you learn in the next slide, which I'm not going to show it, is a complicated formula, which you don't need to remember. And even in advanced textbook, they would just give there. And then there's to the rationale behind this, I think it's rather complicated to understand at our level of math. Okay, so we just take this function as given. What I just want to remind you is you would only take the integer value for this function. Okay, you just forget about the decimal because this is called the round down operator, right? Or the floor function. And that is what we have. And the next is about the paired population. Okay, before the two tests is basically focused on the two populations are unrelated, and here is the sample where actually each observation can be matched, okay, to another one. Okay, so that is what we call treatment effect. Okay, and that's before and after idea. Okay, so in that case you actually want to capture the difference, right? Because you want to see the meaningful thing is about the difference in this context. Of course, you may still care about the mean, right? Difference between before treatment or after treatment is overall measure, but usually the thing you care most is the difference between them, right? Because you can match, then you can see whether if you think x1, x2, they are meaningful difference, then the difference is meaningful, then you will use this technique, okay? And because to take a difference, it's just a single number, and this number, if it follow the bell curve, that's a one sample test, right? It's just nothing new, but just one sample test. So that's why nothing new, but just the standard T-test, okay? And do remember that everything is pair. So N1 is equal to N2, which is equal to N. So that is the framework that we have been using. Okay. So I guess this is the one I want to talk a little bit more, and then I will to the F, and then let's end this topic. So here we have proportion difference, okay? So just to remind you, what we're doing here is basically talking about two independent population. We are trying to see if the proportion are different, right? For example, you may want to see if there's difference between Hong Kong Island and Kowloon Peninsula in terms of the shopping habits, right? So do they go to online or not going to online, say, for example? Or you want to see if, I think we have many colleges, right, in CHK. Maybe you want to compare the original 4 colleges and the new colleges, are they different, right? Say in terms of spending habit, in terms of hall culture or whatever, right? So that would be the thing you want. And one thing you want to remind yourself is when we talk about proportion, the key difference or the key benefit is the mean and the variance are related. If I know the mean or I know something about the mean, I would have something can be said about the variance. Okay. In this particular case, we care about the difference of two population mean, right? And in the particular case, if the null hypothesis said if they're the same, okay, 0, okay, which means that pi 1 equal to pi 2 equal to 0, sorry, equal to pi, okay? That means that this is exactly, not this one, sorry. The numerator are the same, okay, because they're the same pi. So that means that we can have a, we can estimate pi. That's fine, right? We can just use P to estimate this, okay? We don't need to estimate P1 and P2, right? There's no need to estimate P1. You use P1 and P2 to estimate pi 1 and pi 2. Okay, we can do that. That's no problem, but that is not the best way to do. So the best way to do is to combine it, right? Because if under the null hypothesis, they are equal, right? That means that the number of people who have certain characteristic in population 1 is same as 2, then you can just combine them as a single population because there's no difference between them, right? So that's why it motivates what we will see in the next slide, right? Instead of estimating pi 1 and pi 2, we can just go for pi directly. And how to estimate pi? Just simply P. And this P bar is given by actually how many people you are sampling, right? From the 2 population, which is N1 and N2. And actually how many people have that characteristic, right? This is how many people you got, right? From population 1, and this is how you get from population 2, right? Do recall that if you can use this as well, right? You can use either this one or you can either use this one. Okay. You can use this one, you can use this one, or you can this one to estimate pi. But as we learn which is better, turn out to be the P bar is the best. So that's why we use the better one. Okay. So it is okay to use P1 or P2 because they also a good estimate for pi. but which the best among the three will be used P bar. Is that clear? Because they also measure the same, also all of them are measuring proportion, but it's better combined, right? Because that is give you the most accurate description. Is that clear? Okay, I hope that is okay. So that is the reason why we end up in the formula like case one, right? So the case one, you have the same variance, right? So this is the variance, you just put down there, right? And that is normal. Okay, because the reason why it's normal, because for the, you don't have to go to T because you don't need to estimate the variance. Okay, that's why it's normal. Okay, because this is what we call, indeed it's actually binomial, right? But it's an approximation binomial. Okay, now I guess it's okay. We can go to the example to see what we have. And again, I just focus on two side tests. Okay, one side is similar. Okay, and do note that when we do confidence interval estimator, okay, we would do it when actually we reject the Z.TEST, right? If they're different, it's meaningful to measure how much different they are, right? Because we reject the H null, right? So that's why you cannot, when you calculate the margin of error, you cannot use P hat. The reason, again, I repeat, is you are estimating the confidence interval because you reject the idea that they're the same, right? Otherwise, if you don't reject now, why are you predicting this, right? Why are you estimating? Because the hyper testing show they're the same, so there's no need to measure, right? The difference will be zero, right? So that's why we be careful of this particular part. Okay. Now, I guess we can go to this. Okay, example. Okay, and this example is a straightforward application of what we learned. Okay. So first we have two population of binary data. The first one is have sample size 50, so N1 is 50. Okay, and proportion is 6, so this is P1. Okay, and we have N2, which is 40, and P2 is 6.7. Okay, so, and maybe I open a whiteboard. Okay, here. Okay, so what we have here is, let me write down this question thing first, is 50, and 2 is 40, and P1 is 0.6, and P2 is 0.7. Okay. Okay. So this is the question we have. Okay. So so that means that how many people are actually shown to have the characteristic, right? Actually 30 people, and X2 is actually 38. Okay, so that is the first thing we know. Out of 50 people, 30 people actually have that characteristic. Okay, and that's what we have. And the null hypothesis, right, is saying pi1 equal to pi2, right, and x1 is pi1 not equal to pi2. Okay, so let us try to check it out how we are going to proceed, right? And what we have here is we have P1, okay, and this is sample proportion, right? Under when n is big enough, right, you expect a bell curve, right? And similarly, we would have the same thing for population 2. Okay, the P2. I don't know where it is, but There's another bell. Okay. So the question, what we care is not the separate P1 and P2. Rather, we actually care about the absolute difference, right? It's care about P1 minus P2, okay, or P2 minus P1, doesn't really matter, okay. And the bell difference is still a bell, right? So this we have the mean will be just different, right? P1 minus P2, okay, and still a bell. Okay. And remember the variance, right, will be just adding up, right? So the variance for this one, right, will be P1. Say maybe the variance of this will be just pi1, 1 minus pi1 over n1, right? And here we have pi2 minus pi2 over n2. Oh, sorry, I should use the blue color. Okay. Pi2, 1 minus pi2 over n2. Okay. And since they are the same, right? Sorry, since they add up, right? So you would expect the variance like this. Right, so this is what we have here, right? So now we have what we do is under H null. H null is what? H null means pi1 equal to pi2. Okay. So what we have is actually this is 0 here, right? And it's still a bell. Okay. And here we have pi times 1 minus pi over n1 plus pi 1 minus pi over n2. All right, so that is what we have. Okay, so now what we have is the following. Right, look at data. Here, what we get is, I don't know, 0.6 is here. Right, this is what data tells you. And here is 0.7, I don't know. Okay. And kind of difference now here is like negative 0.1. Okay. So we go down, same here, negative 0.1 as well. Okay. So the question is it far away enough, right? So we want this. Okay. It is alpha over 2, alpha over 2. Okay. So we want to see if the negative 0.1 is fall within this region. Right. So that's the idea. Right. The problem, one of this problem, actually, you may see is pi is something unknown, right? It's a normal, it's a bell, but pi we never know. Okay. So should we use t? Right. The question probably you would ask in your head, right? Why don't we use t? The reason is actually turn out you would agree if n is big, which will be true for proportion case, and that even use t end up no difference when you have more than 30 to 40 something, right? So that's why look at all the textbook, they just simply use the proportion, so use the z. Basically, they just assume the bell curve continue to hold, right? Of course, I mean at the beginning already from this part is already approximation, right? Because they should be binomial, right? So already putting a bell is already a approximation. So approximation anyway. But turn out to be this is okay because usually when the proportion, the sample size is always very large, right? It's 11 less than 100. I mean, I guess you ask yes, no question. Well, it's very rarely you less than 100. So even you talk about T, actually no different. We look at the T table, right? So look at T table, and usually it's not a big deal, okay? Of course, I have to tell you that this approximation, why we still keep the bell, even though the pi we don't know, okay? So, yeah, I mean, I'm not going to go against the world. We impose a different thing, but this is the textbook use it. So in case you find a logical gap there, yeah, that's a logical gap. But the reason why we still do it is because in practice it's not easy. Okay, so that is how they do it, and how you get the pi, right? Pi is just simply because you put them the same group, right? So just 30 plus 28 over 50 plus 40, right? Just actually the number of people actually having that characteristic, okay? And then you just go to the bell, assume the bell continue to hold, and then you just look at that. Okay, so that is the goal for that idea. Okay, so let's get back to the question. Okay, so here we look at this is what we have, right? Actually turned out to be 58 over 90. Okay, so that is what we have here. So this is actually 58 over 90. Okay, and then let's check out the next. Okay, so here what we're going to do is trying to look at the Z score. Okay, look at the Z score. So what it is doing is all right, as I said, you still think about this is a normal, right? So it's a normal CO1, just look at the Z. Okay, okay, this is 0. Okay, and once you transform this, is just subtract from the mean over the square root of this guy, right? And turn out that this guy is according to this formula, right? This is P hat, right? This is 1 minus P hat, right? This is N1, this is N2, right? And this is negative 0.9, right? This is P1 minus P2, okay? So it's negative 0.9, okay? So let's see the idea here, right? This is negative 0.1, okay? And go to this Z bell, normal bell, is negative 0.98, okay? So we want to check out this area, okay? If this area multiplied by 2, is it bigger than or smaller than alpha? Okay, so how can we find this guy, right? And probably by now you should not be surprised how you can find this area, right? This area, if you put in Excel, will be 2 times, right? The norm as this, right? Negative 0.98, comma, true, right? So let me do the Excel. So it will be 2 times norm as dot this, okay, 0.98, and then true, okay. So the p value, okay, is 30%, okay. So it's way, way, way too far, so we can't reject it, right? Even though you use 10%, 5%, 1%, you can't reject it, okay? So it's too, that's why I see it, right? So it's here, you can see it's way, way, way too big, the p-value, okay? So, and means then they're different, okay? They're not different, okay? They're not different enough, okay? So you can also use the t-table, right? I'm not going to repeat this, but you know the 5% will be 1.96, right? And actually, you know, this is, if you, maybe I just still do once again. So here, right? 1.96, the 5%, right? It's way here, right? If you try to see the 5%, right? The alpha over 2 thing, right? This is negative 1.96, right? So that means that you really can't reject, okay? And as you can see, I really can't reject. Actually, if I can't reject the confidence interval, it's not that meaningful. You can still calculate that, but it's not that meaningful because this thing will include 0 if you calculate the interval. But nevertheless, we can still calculate that. Just to let you know, this and this are very close to each other. For example, you take the numerator, it's actually here, right? And you look at the denominator, it's actually not exactly there, but the numerator is right here, but just this guy is different, okay? So this is not the same, okay? And this is still the same, okay? So do note that this is not the same thing, okay? The reason why, because this is not exactly right, okay? So better not to use it, okay? In general, okay? Is that okay? Unless you know they're the same, then you can use this one, okay? If you need to make assumption that they're the same, come from the same thing, then you can really use it, but that is not compatible when we talk about measuring the difference. So that's why we have to use what we have seen here. Okay? Is there any question? Is there any question? Because it's basically just applying the formula. Something, but is that okay? Any question? Okay, if no, then I will talk about the F.TEST. So that one is also, actually it's rather simple, the procedure, okay? Each is easiest thing, I would say, for the hyper-testing, okay? And the idea is very simple. Let me just draw it again, okay? The diagram. So I have two population, which is independent, okay? Population 1, okay? And I have sigma 1 square, okay? And I have another population here, okay? And they're independent, okay? So which means that their variance are unrelated, okay? And what we are trying to test is whether they are the same, okay? And why it's important? Because you want to see if they share the same variance, is to see, say, for investment, you want to see if they share the same risk. For quality control, you want to see if the two machine or two method actually produce the same quality, right? Because quality are usually measured by variance, so how well, or the precision, or how well the machine is doing, right? There are many scenarios that we use this as. Also, I mentioned variance is also measuring the precision of mathematical model, right? You talk about machines, which is a physical model, right? The model that exists in the real world, but you should consider the case of how well two different statistical or mathematical model works can also compare the variance. Okay, and and which we'll talk about on NOV later today. Okay, so how do you test this particular guy? Okay, how to test this? The idea is same as what we have said, right? You got a sample here. The sample will give you S1 square. Okay, and you also got another sample here. You also got a S2 square. The test statistic is called F. Okay, it's called F. Okay, which is simply S1 square over S2 square. Okay, and if you recall, F actually usually is called small f, right? Small f here. Okay, this number. F actually compared to T only you have only to check. T only have one parameter n-1, right, or n-2. Okay, here F actually have two things to check. Okay, which turn out to be you will check n1 minus 1, comma n2 minus 1. Okay, and here actually I take n1 of sample, I take n2 of sample. Okay, so what table I'm checking? F actually involve two different numbers. Okay, so in case you are not entirely sure, I would probably want to go to the F table on the web. Then you can you will see what I mean by two different things. I just randomly pick up this one. Okay, as you can see, in this particular example, the F table actually gives you the right hand side, and they fix already 90% for this one. And the column, so the row, so the columns represent the DF1, which is the numerator, and DF2 is the denominator. Okay, so this is two-dimensional one. So that's why you can see they have a very long table. So you have 0.1 here, and that table is 0.05. So this is usually what we want, right? And this table, yeah, is rather complicated, right? But of course, if you have Excel, then everything just you're done, right? Just one click, then you are done. But same as F.TEST, right? F.TEST, you input the thing as you do the T, and later I will show you that it's somewhat easy. And probably you would one thing you wonder is I put the F is 1 is the first, 2 is the second, right? One's numerator, right? You probably would ask, what if we do this guy? Do we get the same result? Yes, you get the same result. Okay. If you do this, but this will become F2 minus 1, F1 minus 1. Okay. So regardless of which one you put, the same result. So there's no bias over one over the other. Okay. So actually we'll show the example that both of them will give the same result. Okay. Because this is the math idea that Fmn is same as 1 over Fnm. Okay, so that is the same. The same thing. Okay, we reverse it. The thing just flip. Okay. Now I guess this giving you enough preview. And the only thing that complicates this object is the F by itself is not symmetric. Okay, so the only difficulties compared to this is very simple, right? The only difficulties is F usually look like a symmetric thing like that. Okay, this is F. Okay, it's come from 0 because the ratio cannot be negative, right? So start from 0, it looks like this, right? And usually you have to look at alpha for 2 here and alpha 2 here. Okay, so you have to look at left and right, okay, and check carefully. Okay, so that is the only thing that is getting more complicated. Okay, so I guess I hope I can do one this and before and have a break and then go to the other case. Okay, so for this one, genetically we focus on 2 tail tests. Okay, So, but you can easily imagine how can you do one tail, right? So, but it's very simple. Here I have the case where, why it's not doing that, or why? Let me see. Oh yeah, because I'm here. Okay, so so I have an N1, right? It's 50, and S1 square is 30, right? And I also have N2 is 40, and S2 square is 20. Okay. So F.TEST is very simple, right? Just the ratio of the two, right? So that's very simple. It's 1.5. Right? So what is difficult here, right? Because there's nothing, this is very simple, right? Because it's just basically the F here. F is, if you, this is 49, 39, okay? And look like this one. Okay. And what we have is somewhere 1.5, okay? And we want to see is, I put alpha to here, alpha to here, okay? Is the red one is going to belong to in this brown region or not? Okay. And either we can use p-value, okay, or you can use critical value method. Okay. So let's use the p-value. Okay. The p-value here is little bit tricky. Okay. The reason is you don't know 1.5 is on the left-hand side or the right-hand side. Right? It's not clear you are, because before p-value, right? Look at this to the extreme case, right? You know whether left and right, right? In this one, you do not sure left or right, okay? To do p-value, which usually you are not required to do it, but if you ask to do p-value, how can you proceed? Okay, you calculate left and right, okay, the area, and then you pick up the one that's smaller and multiply by 2, right? Because if you take up the larger one, multiply by 2, then you more than 1, right? Because the left-hand side or right-hand side is up to 1, right? So you just pick up the one that's smaller and multiply by 2. So that is what I have in the previous slide when you do the p-value. You just pick up the smaller one and then multiply by 2. Okay. So how can we do this here? It's very simple, right? You can look at the area. Suppose this area. How can you get this area? It's just F this 1.5 is number, and you put in degree of freedom 49, 39, right? 49, 39. Okay. Okay. And you look at this number. Is it less than 0.5? If so, yeah, go ahead. Multiply by 2. If not, subtract from 1, you calculate right-hand side and multiply by 2, the same thing. Okay? So that is the standard procedure. So let's do it, okay? And then, okay, that will be F this, okay? And 1.5, 49, 39. And true, sorry, I forget the true. Okay, because of this. Okay, so you can see this is 0.9, okay, which means that actually 1.5 is deep inside the region. So that means if I go back to here, okay, right, so let me erase it to put true there. Put true there first, okay. So indeed, this is actually somewhere way inside here, or here is, all right, because the left-hand side is 0.9, so it's very deep inside on the right-hand side, okay. So how do the p-value, right, is you would be doing the, instead of doing this guy, you would take 1 subtract this guy, And this is the right-hand side area, right? And what you want is you want to multiply by 2. Okay. And here the p-value, what you get is 90%. So you really can't reject. Okay. So of course, if you think that in this case you think the p-value is actually rather clumsy, right? And in that case, you actually want to look at the critical value method, right? And you have 2 critical value, right? So one is left-hand side, one is the right-hand side, right? The left-hand side one will be just the F dot inverse, right? 0.025, 2.5%, right? The left-hand side is 49, the right-hand side is 39. Okay. So this will be the left-hand side, okay? And the right-hand side will be the F dot inverse, okay? 0.975, 49, 39. Okay. So these 2 will be the value, right? So basically you look at this case is this is 1.84, okay? And this is 0.55, okay? So which tells you, okay, indeed is this particular case, okay? So you really can't reject, right? Because your value is not in the rejection region, okay? So you can't reject at 5% significance level that H now is wrong, right? You can't reject it. So you have to keep your idea of H now. Okay. So that is how you would do, okay? And this critical value, right, you can easily check from the F table, okay? Maybe I can show you here, right, how you can do it, right? Is you would check this right tail 0.025 is 49. You can have 40, you can use 40 here, use a smaller one, and F2 will be fertilize something like 4, something like here, okay, something 2 point something, or 1.93, something like that, okay. And you also have to look at this is the right tail. You have to look at the right left hand tail. That is I mean, it's easier to use the obviously easier to use p-value method, right? Because table is not very convenient. But I hope it's clear now. You learn the very last piece of hypothesis testing. Okay, the last test. It's very simple. The only difficult thing is you do the p-value. Okay, you pick up the smaller side, multiply by 2, right? Because you don't know where you are, right? Before you the t and the z, the p is very simple because you know which side is smaller, right? You only go to the other way around, then you're done. Is that okay? Is there any question? Okay. And after the break, we do the other way around and so you did the same, and then we're done with this. And then we'll do some Excels, and then we'll start on over. Okay, we'll do some Excel afterward. Okay. In the meantime, I go around to see if you have any questions. Let's have a 10 minutes break. That is actually there's a more advanced version. But you always need to see that. It's implied. Key values are like good you are. So that's why I changed it. I think our idea to define what I hope that game is define it. One side. So good. I guess I go around and then I didn't saw particular issues here, so I guess I can do once again. Okay. Or I guess I've a little bit typo here just to remind you is legacy, because someone asked me actually this has a little typo here, the 6 here. Okay, so that's a minor typo. I mean this already covered already, but I just make sure that maybe this is more than. Okay, so that's a minor typo in this page. So make sure that I mean, I think we discussed it. I don't think it's a big issue there. Just make sure when you go to read this out, you don't have a big problem. Is that okay? Okay. And as we conclude, okay, and let me quickly talk about this one. Okay, you can see you can reverse the S2 square over S1 square. Okay, and that you get a number which is 2 over 3. Okay, and you can do the same, the critical value of this and critical value of that, right? And you can see again, this is between these two values. Okay, so you can't reject. Okay, just to remind you that if you are two-sided test, right? If your test statistic is between these two critical values, you don't reject. So this is the same as what we cover so far already, right? Because critical value tells you the boundary of the resonant region, right? The 2n. If more extreme than these two values, then you reject. All right. So I guess that should be fine. And the p-value will also give you the same result. So I'm not going to repeat that because the same thing. So I guess the remaining time I will go over the Excel, okay? And then you have time to talk about ANOVA, okay? So here we have a bunch of links, and you can take a look if you have any issue. So I want to talk about Excel because Excel actually gives you the tests you want, okay? The first one is the function called Z.TEST, okay? This one basically do the following, okay? If you give the data, okay, which is 2, 2, 3, 3, 4, 6, okay? And then if you put the mu, which is the mean, you test whether it's equal to 4 or not, okay? And then you give the population variance, so standard deviation, they give you the p-value, okay? And maybe it's good to show you this is the case, okay? So let me do, this is called the Z.TEST. Okay. So I have the data. I don't know. I just repeat what we have here is 2, 2, 3, 3, 4, 6. Okay. 2, 2, 3, 3, 4, 6. Okay. So this is data. Okay. Oh, where's data? Why? Where? Oh, I see. Okay. So how this is data and how can you proceed, right? And I want to do a Z.TEST, right? This is data. Okay. And the data, what we have is the null is 4, right? The variance, the sigma is 2, right? So mu is 4. We want to check. Sigma is what? It's 2. Okay. So this is what we want to do. Okay. And actually, this is with the data you are looking, right? Because this is what usually the data you would have, right? This is the data, and this is hypothesis. This is someone give you the sigma. Okay. So so let's do it from scratch. Okay. And then we can see how the Z.TEST give you. So we can calculate the bar of x, right? The mean, right? Bar x bar or x bar, right? X bar is what? X bar just the average, right? Okay. So this is the first part. Okay. And we can do a Z, right? Okay. Do note that was n. N is number of the data. So let me do the what we call the count. Okay. Let's count how many of them. Okay. So this is maybe a yellow, the one that see, then let me also save the file in case it dies suddenly. Okay, so this is the thing. Okay, how do you calculate the z-score, right? The z-score, if you remember, just one sample with just this number, okay, minus the hypothesis, okay, and you divide it by sigma over root n, so it is sigma over square root of n. Okay. So what is this formula here? Right? Just recall is x bar minus mu over sigma over root n. Okay. So this is C4, right? This is C1, right? This is C2, and this is C3. Okay. So as you see, this is the number, okay? And can you calculate the p-value? Okay. And if you do the p-value, the left tail, right? The p-value. If you do a left tail, the left tail will be simply just the this is norm dot x dot this of this guy, right? This is the value on the left. Okay, this is the value on the left. Okay, and if you do the p-value on the right, will be just 1 minus what we have here. Okay, and of course, if you do the both tail, right? If two tail, then you just take the smaller one and times 2, right? So that is okay. Or if you like to be more mathematical, you take the minimum of the 2, right? Right. If you want to be a more engineer style, right? So that is the p-value. Right. So this is how you would do if you given data, you given sigma, how you do the Z-test. Is that clear? Okay. So this is exactly what you will be doing. Okay. And everything is in the slide already, but I just do it quickly. So, and also I also have used the Z.TEST. Okay. So how can you do this directly? Okay. You can do the following, called Z.TEST. Okay. And you just put in the data, which is A2 to A7. And then you put what is the mu and what's the sigma. Okay. And that's it. Okay. As you can see, it will automatically give you the right tail. Okay. So the Z.TEST gives you the right tail. Okay. And the left tail, of course, you know how to do it, right? 1 minus. And how you do the two tail, it just you just take the minimum of the left and right. Right? That's how easily Excel can handle everything for you. Is that okay? Is that clear how we are going to handle this? Okay. So this is a Z.TEST. So this is a one sample Z.TEST. So let me do the one sample T.TEST here. Okay, the same thing. So let me do it, and then what I do is I copy this thing. Okay. Copy this. Instead of the T.TEST, I focus on T.TEST. Okay, one sample T.TEST. So how we do one sample T.TEST is we don't have sigma anymore, right? So this is gone. We don't have this sigma. Okay. So instead of sigma, then we have S. Okay. So let me get this out. Okay. We don't have this sigma. Instead, we have S. Okay. And this is no longer yellow. Okay. Let me make it green to make sure that you know what's going on there. And what we want is, instead of putting an S, right? As what we have is using this STD EV S, right, of this one. Okay, so this is the sample SD, right? So this is no longer the Z, but rather become a T. Okay, so this, the first line, S no problem, N had no problem, X bar no problem, but now we are no longer using the Z instead of T, but the answer the same, right? The only difference is this is no longer sigma, but this is S, right? And beside these changes, right? These auto changes because no longer you're using the norm, right? Rather you're using the T, okay? And what's degree of freedom? Which is 6 minus 1, right? So this is the changes. Okay. So this is the what you get is 1.6. Okay. And left is all the same, p-value the same. Okay. And this Z.TEST also different because you don't give the last entry sigma. Okay. And there's some problem with that. Okay. Okay. So I guess they use something different. Yes, they are different anyway. Okay. There's some difference because the Z.TEST they don't give you. So maybe I just don't use this one. We don't have this line, so just to make sure they don't confuse. Okay, so for T, you have to do it from scratch. Okay, so this is how you get the one sample Z.TEST and one sample T.TEST. Okay. Any question? So the next thing that I want to talk about is the function we call the this is one sample T.TEST. Okay. So what we have is the two sample T.TEST. Two sample T.TEST. So this one actually cover all the things we want to cover. Okay. So let's see how we can do that. Okay. So we have two sample T.TEST. Okay. And let's see what kind of data we got here. Okay. Let me erase the drawing first. Okay. So we have two sample X1 and X2. Okay. Sample one is 4, 3, 4, 2, 5, 6, 7. And the other one is 3, 2, 6, 7. Okay. So these are the data. Okay. These are data. So what we want is to apply a T-test on it. Okay. And here we can see we have equal variance. Okay. Equal variance is the last element is 2. Okay. And if we want to not have T-test non-equal, then 3 is at the end. Okay. So that's a difference. So here we have equal variance. Okay. Equal variance. And I want to calculate the p-value. Okay. And how do we proceed from here? Right. So the first thing is you want to calculate the x bar 1, okay, and x bar 2. So which are the average of the first element and average of the second element. Right? Maybe I. Okay. Oh, interesting. The same. Okay. So you can also calculate. Maybe I just put the formula here. Okay. This is the average of these two. Okay. And I also want to know the sigma. Maybe we know the variance is better, right? Sigma square 1. Okay. Sigma square 1. And we have sigma square 2, okay, which is given by variance dot S of the first column and variance of S of the second one. Okay. So these are the two cases. Okay. And then you need to calculate the pooled variance, right? The pool variance. So it's S square P, okay, the pool variance. And pooled variance is the weighted average, right? So before we do that, it's better to have N1 and N2, right? N1 is simply you count how many of them, right? Okay. And N2 is just count how many of those. Okay. So that's how you calculate that. Okay. And what's pooled variance is the weighted average of these two. Okay. So we just take what we learned is you take N1 minus 1 times sigma 1, right? Plus N2 minus 1 times sigma 2, okay? And the whole thing actually divided by, okay, N1 plus N2 minus 2, okay? So this is how you calculate the pool variance, which is right because it must be between 3.5 and 5.6, right? So now we can calculate our T-stat, right? The T-stat is simply just, if you remember how we calculate the T-stat here, the T-stat is x1 bar minus x2 bar, right? And take a square root, SP square over N1 plus SP square over N2, okay? So what we have is just, actually, it's just 0, right? You don't need to calculate. But anyway, let's do it in case it's different, right? So we have this minus this guy, okay? And divided by square root of SP over N1 plus SP2 over N2, okay? So this is the T-stat, okay? And even though without calculation, you know the p-value will be 50%, right? Because the left-hand side and the right-hand side are the same, right? Actually, p-value the left, right, will be just T this, right, of this number. Degree of freedom will be N1 plus N2 minus 2, okay? And then true, okay, 0.5, okay? And you can do the same for the right-hand side, right, and the both tail, okay? Then you can also do the p-value, right, okay, which is 1 minus this guy, right? This is also the right. Okay, and then you can do p-value of 2 tail, okay, which is given by 2 times minimum of this 2. Okay, and luckily for this one, okay, you can use what we call T.TEST, okay, which is T.TEST. Okay, you put the first data set, second data set, you can tell, you can do the right tail, you can say we are doing the equal variance, okay? So that is how you get this guy, okay? And then this is the right tail, okay? And then you can also do the T-test and then do the 2 tail, okay? Which is simply T-test, okay? Get the first set of data, second set of data, get a 2 tail one, and get a 2 one, okay? Okay, so this, let me go up here, okay? So this is the one that is in the function, right? So you just tell them what data you have, right? If you 1 tail, you tell them 1, right? 2 tail, you give them 2. 2 is mean the equal variance, okay? So here, you can see how you do the 2 sample T-test, right? This is equal variance. And the unequal variance is the same thing, right? Except things become much more complicated, okay? So maybe I do the unequal version as well, okay? Unequal version, okay? will be complicated, okay? A little bit more complicated, okay? The thing is, we don't need to calculate this guy, okay? This is no longer relevant. This is not relevant at all. Okay. So we don't need this guy. We don't need this guy. The reason is when you have unequal, no SP. This one is S1 squared. This is S2 squared. Right? So we really don't need that particular guy. Okay. So this guy is not needed. So I just strike through. Okay, we don't need this one. So what you need is just D4 over D5. Okay. Okay. And the complication that you try to calculate by yourself is you need to calculate what is the V. Okay. So maybe I just take it again. What's the V? And the V involves a very complicated thing. Okay. The V comes from this formula. If you still recall, the V is something crazy. Okay. I would say. So this is the formula. Okay. S1 squared over N1. Okay, let's do that. Let's do that in our formula here. Okay. So that would be S1 squared over N1. Okay. And this is square. And you do the same for the S2, right? It's just S2 squared over N2 and then square. Let's see if I'm right or wrong. Yes, this is the formula for the numerator. Okay. And you do the same for the denominator. Okay, so this is the numerator. Okay. So it's super complicated. Okay. You have again to put in the S1 over N1 again and take square, and you divide it by N1 minus 1. Okay. And do the same is S2, okay, D5 over N2, okay, and raised to the power 2, and then you over, which is crazy, N2 minus 1, okay, and I get the wrong side here. So just here, I get a bracket. Oh boy, right, I typed the wrong thing. Okay. So it's around 3. Okay. So you would, this is around 3, so you use 3. Okay. So so what you do is you use the 3 here. Okay. So everything that follows. Okay. So the only difficulties is this guy. Okay. This is the most difficult part. Okay. And you can check out this formula, exactly the formula written down in the test. Okay. Within in the slides. Okay. So the good thing is if you use Excel, okay, if you have the raw data, then you can see I only need to change this to 3 at the end, then I'm done. Okay. So this is the last, is the 3. I am just, it's data and I just use 3, then I'm done. Okay. So I don't need to do too many things. Okay. That's how I can get the T.TEST. Okay. Is there any question? So basically, is this automatically give us what we want, right? Because you have data, you do a T.TEST, right? Just put in the data there. You tell them one tail or two tail, whether it's a different type, then you're done, right? So that is, it's nothing but very simple, right? Is that okay? So lastly, I want to talk about the F.TEST. Okay, that is also very simple there. Okay, F.TEST. Okay, F.TEST is very simple because you don't really need anything, right? You don't need X bar. Okay, you just need sigma, right? So we can just simply delete this. Okay, and let me shift anything upward. Okay, so F.TEST, you calculate the variance. Okay, and the F is just simply, okay, the F is just simply the ratio, right? The F is just, okay, the F is simply just F1, sigma 1 over sigma 2, okay? And then the left tail, the p-value will be just F this, right? This value, you put this -1 and this -1 and true, okay? And this gives us already a p-value, right? And you can take 1 minus this one will be the answer, okay? So just one very minor final formula is the F.TEST, okay? You just do the F.TEST, okay? You just give the left and give the right, okay? And what they get is the, I think the minimum of the two. Okay. So that is the formula, the F.TEST. Okay, I think two tail. Okay. So that is what we have. Okay, so that is, we cover everything in our thing. Okay, so I upload this to the blackboard, and later you will see in the next class we talk about how to add in. That makes things even easier. Okay, but here is, I think, is enough Excel for you to handle everything. Okay, sorry for 1 minute delay. I will see you on Thursday. Yep. Oh yeah. It's 4 here. Okay, that makes sense now. Thanks. Otherwise, I think it's 0. It's not fun. Yeah. Okay. Thanks. Thank you. Bye. 好，做人做人。